So I'm going to talk about, and we are going to talk about our project to build Turing universal molecular machines using Rotaxane automata. So what that means, first of all, Turing universal basically means that it can run any program, that any computer is equivalent to any other. And so then the existing implementations, there are various kinds of things that have been built. There's some existing implementations along these lines have been built using DNA tile self-assembly, which is rate limited by diffusion and reaction rates. Whereas what we plan to do, and we'll show you the details, is using Rotaxane to actually capture modifiable state and then use simple cellular automata rules for logic that can be easily encoded into molecular structures and then just replicated and tiled in a 2D fashion. So this gives us a much faster cycle time for doing the computation. It can run in parallel across all of the cells. It can also be energy efficient and gives higher resolution and higher density than you might get with DNA tiles, where a cell might just be a few nanometers in size. So some of the applications here that can be used to embed complex logic in molecular devices, for materials patterning, for doing drug targeting, for building dynamic materials that respond to their environment. Some metrics that we'd use to sort of evaluate how well we do as we go along is to look at the computational complexity, because the more complex the rule, the more complex a program that you can build, and then just the overall capacity, which is based on how large a grid we can build. So the basic idea is that we build a grid structure where the lines in between the grid have Rotaxane, have cyclodectrins on them, and then the logic is embedded in the nodes within the grid. So the state is encapsulated along whether these are up or down or left or right, and then the logic propagates from the input to the output, where the state of this then determines what happens to these, the state of these two determine what happens to those, and so on. And so the state propagates along through. So the logic is effectively, the logical update rule for the cellular automata is built into functional groups that we've attached to these nodes in the network and onto the cyclodextrins. So these little functional groups and the way they interact determines what happens when these go here and then expand on, and this will then determine what happens to these two neighbors, and then these two neighbors will determine what happens to that. And this will sort of, the computation will flow across the grid. So now let's get into some of the chemistry of how that's implemented.
Okay. Thank you. So our group would like to use Rotaxane, one of the mechanically equivalent molecules to build our Turing. Okay. Turing machine. The external stimulation, aka input, is using the light by different wavelengths. So different wavelengths of light will be different. Okay. Different type of input. So, for example, here the light can be triggered the cleavage of the disulfur bond, as well as changing the formation of the azobenzene. And the azobenzene can generate very good unidirectional motion, which Professor Crady showed many examples yesterday morning. And here we can see that we are using the dinaphthalene chrome ether to use as the microcycle to go throughout the Rotaxane dumbbell. And this naphthalene ring can also highly functionize in order to produce different kind of external output. And so here's some of the design that on the phenolene ring, you can have different types of the functional position. And this kind of functional position can act as different signal propagation by the dynamic disulfur chemistry. So different type of them can act as different type of component of this computational machine. And this will go throughout the framework of the Rotaxane. So I just raised up two examples of the logic gate I just designed by a 3 years old kid's draft here. that you can see the head and the tail are highly functionable and can go through a head-to-tail function. So all of them, the component of the logic gate can link it together by the functional group at the end, at the head and the tail. And here the end, if you give the input such as light or both ends of the branches, Rotaxane, two of the smaller ring will generate the unidirectional motion and combine together at the center part and generate the disulfur bond. And this will have a stereo bulky to drive the middle part of the chronoeder to move to the right-hand side part. As you know, the right-hand side can also link to another head of the new logic gate that can continually generate more complex system. And the design of the all logic gate is very similar, but at the core, itself has a sulfur. So you can only need to give one of the input rather than two input on both sides. So that can drive the similar stereo bulky and drive the microcycle go through to the tail and generate the full process of the signal propagation. And we will going to detect the output by the optical imaging, which will be introduced by Alex.
Yeah, so just like we have several strategies to make the logic gates to mitigate the risks there, we also have several strategies for reading the output to mitigate those risks. The first one we have in mind is the using DNA paint, which is a super resolution technique. If we can label the rings and or the output nodes with DNA, then we can localize them with super resolution, which can be as high resolution as 5 nanometers. Probably for our first go, we can have a simple kind of reaction-based trigger output. So at the output node, we can have the thiol react with a dye that changes its color when it links with the thiol, and that would give us a way to quickly look at the output in there. And we can also do sort of a small molecule super resolution technique where we can link a spontaneously blinking dye to the output node and then have the thiol release a PET quencher. So we have several strategies to mitigate the risks there. And finally, we can do AFM and SEM to kind of really characterize the system as we're developing it to make sure that everything is in the right place. And so the tasks, So the tasks, we broke it down into basically 2-year tasks, 4 postdocs per year. The year 1 will focus on synthesizing the logic units, input nodes and output nodes, surface attachment, so we're gonna put this onto a 2D surface and kind of get a total assembly of the grid structure. The milestones will be kind of a demonstration of the single logic gates, as well as demonstration of logic gates in sequence. And then year 2, we're really gonna work on the inputs and outputs, get the whole system working together, develop any hardware that needs to be developed, do the characterization, and ultimately doing the coding, so working with theoreticians and the computer scientists on our team to see what we can program with this and what we can do with it. Future directions, we think that we can, in addition to use light input, we can use inputs from solutions, different analytes, different other ways to do the sensing and the computation. And we can also have the outputs, instead of doing an optical output, releasing molecules. So kind of a real-time computation, chemistry to chemistry type of computation, which might be useful in medicine and other types of applications. We can modify the rules. So we have a couple logic gates now, but we anticipate over the next few years we'll develop ways to make more complex rules and do more complex types of computations that perhaps you can't do with standard computers. And finally, we'll work towards synthesizing larger grids and even more complex logic, and kind of think about the reversible reactions versus unreversible reactions and what we can do with that. We got it. Okay, our team. We have a team consisting of computer scientists, synthetic chemists, a lot of DNA expertise, and some supramolecular expertise. This is our team here. I think we have a strong one. And yeah, be happy to address any questions.
Okay, and questions and comments from our judges.
Okay, I have a couple of questions. So, or comments first. I mean, as a comment, when you define the number of tasks and you put 4 postdocs, I think that would be a yellow light in my view, because I mean, you need to have as many tasks as postdocs that you require for the effort. Otherwise, it's not clear why do you need the personnel that you're asking for. So that's technical, but I mean more formal than anything. But my main question would be, do you have any guess of what would be the limiting mechanism in the entire process for rate, for speed? Because if you're proposing a Turing machine, you have to compare it with other things that are out there that are fairly fast.
I think the limitation, you are raising a good opinion that the limitation will be the speed, since the electric wire will transfer the signal immediately, like light of speed. However, we are using chemical bond and Rotaxane, which transfer that kind of signal will relate to the speed of transfer the microcycle through the dumbbell of the Rotaxane. But we still think about this kind of strategy, build a new method that design and synthesis a new type of Turing machine. And also we can minimize the size of the whole system by good design of the chemical structure.
Okay.
So I had a related question, and it's a bit of a two-part, but do you have a sense of then, what your scale is in terms of, how commented on faster time scales, like relatively what's the order of magnitude, and then you just commented on some of the advantages of your approach. Do you, again, sort of have a sense of the quantitative metrics in terms of what the gain is? So if you're reducing your size, what's the relative scale and the value proposition?
I mean, I think we've had like 4 hours or something to work on this. So I think at the basic level, we're looking at nanometer scale, and however fast we make those reactions go. I think as fleshing this out into a written proposal, we'd go through and work through the initial calculations to bound what those look like. So we'd go through some initial calculations just to figure out what those bounds are. But given the time available today, we weren't able to go through that.
I see this as a kind of an architecture, which is kind of unicellular automata, or something like origami type of architecture, plus you have a building block, which is the Rotaxane, which is a good idea to combine both. But I believe there is 3-4 items fundamental we should check. If this is considered the logic, I think it will be probably a kind of probabilistic type of computing, because with this kind of structure, is a likelihood of 1 and 0 and to be added. It theoretically can be done, but practically, this is what is the possibility that this, probability 1.1, 0.9, 0.99. That's number one. I think this is it should be a configuration for the minimum energy, because there is some kind of concern. Are we talking about system at equilibrium? That may not support this kind of logic. I'm just from a technical point. The third thing about it, which was a problem with this kind of architecture, is there is a propagating error of something is going wrong at one place. Where are we going to catch it? Are we detect it or correct it? As again, these are technical inputs that would have been addressed if there is more time. That's just my inputs.
Yeah, again, the third one I think is something that, as we understand the error characteristics, that's part of the computer science aspect of it. That there are various coding models for actually doing error correcting and error resilient computation to deal with noise within the circuits.
Yeah, but when you have in a circuit one structure that thinks wave would go from left to right, is either you add redundancy to detect it, or you have to live with what is the computation at the end. But again, that's a very low level question, but just to be considered.
It can be overhead much less than simple redundancy if you work through the math. There are a lot of interesting computational architectures for doing that.
Thank you.
Any other quick questions from the judges? Are we done? We are done. Oh, thank you, gentlemen. Let's give them a hand.